Everything we have studied so far has been about fluids at rest. But the AP exam loves fluids in motion. Today is the grand finale of the theory, the equation of continuity and the legendary Bernoulli's equation. We are going to prove why water sprays faster when you cover a horse and why fast moving air actually creates lower pressure. This is basically the conservation of energy for liquids. This maths can look intimidating, but I am going to show you the cancellation trick to make these long equations disappear. If you are ready to see the world like a fluid dynamic expert, let's get started.
So specifically in today's session, we'll be starting dynamics, fluid dynamics.
Yes, sir.
Whenever you see that word dynamics, it means that something is in motion. As specifically we are dealing with fluids, so the study of fluids in motion comes under this particular part of the unit, that is fluid dynamics.
Yes, sir.
Before going ahead, let us recall few properties of ideal fluid. So ideal fluid are those fluid which shows steady flow. Ideal fluid are those fluid which shows incompressible flow. Similarly, the flow should be non-viscous, and last but not the least, it should be irrotational. So in order to understand that how ideal fluid looks like, just try to memorize the flow of any type of crude oil, or specifically called gasoline. Have you seen gasoline being transferred to the any sort of vehicle?
Like some people.
When this massive bag was cut open, the liquid flowing out looked like it was frozen in time. But why? You see, this phenomenon is known as laminar flow. Unlike turbulent flow, where liquids mix chaotically, laminar flow occurs when a liquid moves in smooth, parallel layers, making it appear as though it's not moving at all, even though the liquid is actually flowing. This happens because each liquid molecule
So this is what ideal fluid is. Like it appears to be that it is not moving, but actually it is moving. It is moving in such a way that all the particles follow the path of the forward particle, and the path is so smooth that it actually appears that it isn't moving. So this is what ideal fluid is, and it is kind of important to imagine to understand that how ideal fluid actually looks like. So I hope you are able to imagine that how flow actually looks like. Although in general, in everyday life, we don't actually observe such flow because it is not there, because most of the fluid which we deals with, it's not ideal fluid. Whereas in general, if you observe, there is a tap and you just try to turn it on, the liquid or the water droplet spread across the other path as well, and that is only because of the rotational flow, or you can say the air present inside it, which actually guides the particles to not follow the path followed by the preceding one or the successive one. So that is what this is how idle fluid is different from normal day-to-day everyday fluid we are dealing with. So one thing you have to keep in mind, whatever physics now we are going to study, it is only applicable for ideal fluid. If the fluid is not ideal, the physics we are going to deal with, it is no more applicable to that. So let us try to understand it, and we'll go and understand the whole thing with understanding with equation of continuity. As this equation has a different role and a very important role in understanding Bernoulli's principle, so we need to understand what equation of continuity is first. Let me just give you a very simple idea and you'll be able to quickly memorize. You will be definitely able to memorize because you must have done it in school, I guess. So suppose there is a pipe and that pipe is of different cross section. So what we have to understand here is, as the liquid flows through that pipe and being pipe is of a different cross section area, what we need to understand here is that during the streamline flow of such ideal fluids, through the pipe of varying cross-section area, the product of area and the normal fluid velocity, it always remains constant throughout the flow. What does it mean? It simply means that the mass of liquid flowing throughout this pipe, irrespective of the area of cross-section, it remains same through both the areas. Why we can say that? Let me just give you a very simple and basic example to actually understand it. Imagine that you are watering plant in your house and suddenly you feels like that water is not coming out too quickly. What you will do? You will just press the nozzle of the pipe through which water is coming out. And when you press the nozzle, you suddenly feels that now water is going to a larger distance. Why exactly that happens? That exactly happens because you have pressed the nozzle so that it reduced the area from which liquid was coming out. Initially, the area was like that. Now, what you did is you pressed it so that area reduced. When you did this, the liquid is going to the larger distances. Initially, it is going to a certain distance, but now it is going to a larger distance. Why? Because you have reduced the area. Why this is happening? This is happening because the mass of fluid that flows through the cross section in given time is always same, whether it is the initial one, whether it is the final one. So that is the most important part you have to keep in mind about flow, flow of any sort of ideal liquid. So here that thing can be asked in FRQs as well. So what we'll say, mass of fluid flowing through different cross section, let's say A and B, must be same. So what we know is whatever amount of liquid flowing through that cross section area must be equals to the liquid flowing through that cross section area, another cross section area. So let me just take it as the area of this cross section is A1, area of this cross section is A2. Similarly, the speed with which liquid is going out from here is V1 and speed with which liquid is going out from here is V2. So these are the two things we have imagined. Now just try to think if we have considered a small time interval t. So for any time delta t,
Sir, can I go to
imagine,
the? Can I get some water very quickly, sir?
sure.
Thank you, sir. Thank you. Yes, sir. Thank you.
So for any delta t time, I have imagined that the layer present here initially must have reached or must have covered certain distance. Similarly, the layer present here also must have covered certain distance. So what that distance going to be? So that distance I can mark as V1 delta t. How we can write it? As we know, speed is nothing but distance upon time. So distance is going to be speed into time. So for that first layer, speed is V1, time is V2. So x1 can be written as V1 times delta t. Similarly, x2 for the smaller cross section area where speed must be more than the position or the motion of the layer can be experiencing some displacement, that is V2 delta T. So that is the part we have to understand, that whatever motion we are going to observe, so layer must be moving V2 delta T times for the part B or the cross section B, whereas for cross section A, layer must have moved V1 delta T displacement for the given same time. Now, what is the most important part? That the mass of fluid flowing through must be constant. So let us try to write what is mass. So M1, that is mass of flow liquid flowing through that cross section area, or it is the point A. So M1 can be written as what? What we know, mass is nothing but volume times density, right? What you can write in place of volume? In place of volume, we can write area times length, and density remains same. Similarly, what is area? I'm writing it for cross section area A1. So area is going to be A1. What is length? Length is this, that how much it has displaced in delta T times. So length is going to be V1 delta T. And what about density? Density of the fluid will remain same because we are dealing with ideal fluid. So you can write it as rho. So this is mass of liquid flowing through A, first cross section area. Similarly, for second cross section area, we can write N2 must be equals to A2 V2 delta T times rho. As for ideal fluids, we know that mass of the fluid liquid flowing must be constant. So we can say M1 must be equals to M2, and this is for ideal fluids. So you can simply write A1 V1 delta T times rho must be equals to A2 V2 delta T times rho. So from here we got that A1 V1 is equals to A2 V2, and this is the equation which actually help us to calculate flow rate of a liquid. This is the equation which actually gives us at how much liquid is flowing through a given area of cross section in terms of magnitude. If we try to understand what is the unit of flow rate, we can simply say area is meter square and velocity is meters per second. So unit of flow rate must be meter cube per second. That is important. So whenever you see this unit in a given question, just keep this thing in mind that it is given as rate flow, and it is again only applicable for objects, or you can say the liquid which are ideal in nature. Generally, not all the liquids are ideal in nature, but yes, this one is like that. So this equation is something which you're going to use in Bernoulli's principle, which is our next topic. So the next thing we are going to talk about is Bernoulli's principle. So
Wait, sir, can you go back a slide?
yeah,
So wait. You said M1 is equal to the volume times density, and then you substituted that in. So um, wait, wait, times to length and times density. So then, and then you said M1 is equal to like A1 V1 delta T
times density, that is rho.
times rho. Wait, sir, I'm confused though. Where did you get the other variables from when you were deriving it?
What is mass? Mass is nothing but if we talk about density, density is nothing but mass over volume. So
So
mass is
volume
density
over
times
density.
volume.
But yeah, volume times density.
Volume is what? Area times length.
Oh,
Length times density. Volume is area times length. Now, what is length? Length is basically how much that liquid layer has displaced. So it has displaced by
del.
V1 delta T for
Oh, okay.
first layer. So it is going to be A1 V1 delta T times T. As we are taking, as we are observing the change for similar time, that is delta T for both the layers. So M1 is going to be A1 V1 delta T D. Again, the amount of liquid flowing through this cross section area and this cross section area at a given time delta T must be same, because it is we are talking about ideal fluid. It must be same then we can say that M1 must be equals to M2. So we can write A1 V1 must be equals to A2 V2. So A1 V1, or the product of area and velocity of a liquid flowing through that particular area of cross section, gives us the flow rate, and flow rate is always measured in meter cube per second. So that meter cube per second only came from the product of area and velocity only. What you need to keep in mind is, whenever a liquid flows through different cross section area, amount of mass of liquid flowing through that cross section area through a given or same pipe must be same. It must not be different. If it is different, amount of liquid is different, then it means that fluid is not ideal. But most of the time, the fluid which we are dealing with is generally ideal fluid. So if we are dealing with ideal fluid, the flow rate must be constant for both the cross section areas. Just take this point as in mind. The opening of the pipe, which is connected to the tank, over a tank of a house, it has much more opening, like the area is more. Whereas the tap, which we are using at our home, has a smaller opening. That is the reason why when water comes out from a tap, it has a very high speed. Whereas when water goes into the tank, when we turn on motor to fill the tank, that velocity is not that much. Although it is similar, the rate of the flow of liquid is similar in both the cases, but opening, or you can say the area of cross section, makes the difference. Area of cross section is the reason why water comes out from the pipe, or you can say water comes out from the tap with a more velocity in comparison to with what velocity it enters into the tank, because
So,
area of
sir,
cross section is different.
when we're going to a smaller cross-sectional area, does that mean like, okay, in the cross-sectional area there are less water particles, but behind the water particles, there's a lot of water particles in the water molecules, like in the bigger tank, which means that there's a higher pressure behind it, and the high pressure must go to a low pressure. So is the reason velocity increases because the high pressure
That is
go,
also one of the reasons.
moves to
That
a
is
low
also one
pressure.
such factor. Yeah, that is also one such factor. But here we are thinking from the area point of view. So we'll simply say, if area is more, velocity is going to be less. If area is less, velocity is going to be more. That's all. That is what you can keep in mind. It all depends upon the area and velocity, as they both are inversely related. That is what you have to keep in mind. And why they are inversely related? Because the product of these two things must be constant. That is what flow rate is.
Oh, so the one must when one goes up, one must go down to compensate.
Yeah.
Okay.
So the next thing we have to talk about is Bernoulli's principle. So first of all, we need to understand what Bernoulli's principle is. Any idea like why we are actually studying Bernoulli's principle? What is the significance of this principle is?
Because right now we've only been dealing with static fluids. The Bernoulli's principle allows us to deal with dynamic fluids.
No, that's not the reason.
Mm, oh yes, yes, I remember. Sorry, sir. There was what do you call it? The equation, the conservation of energy, right?
Yeah, now I got it. So basically, for fluids, we don't have any energy conservation relation. So Bernoulli's principle actually gives us the conservation of energy for fluid, for flowing fluids. Before that chapter, before that unit, we have seen the solid objects. We have seen the motion of those particles which have mass, which are solid, which are not flowing. But what about liquids? So is the energy principle doesn't exist for liquids? That's not the case. Then here comes the Bernoulli's principle. So Bernoulli's principle says that sum of all the energies present for a liquid, that is pressure energy, kinetic energy, and potential energy for a per unit volume for any type of ideal fluid is constant. It's constant throughout the streamline. That is what Bernoulli principle says. In the previous units, we talked about work energy theorem, right? What is work energy theorem?
The work is equal to the change in kinetic energy.
Or we should not say that. That is not the work energy theorem. We should say that
Sorry.
work done by all the
Yes.
forces. Work done by
Like,
all the forces must be equals to change in kinetic energy. How many forces do we have? How many types of forces do we have? Let us try to understand. We have conservative forces. We have non-conservative forces, as well as there is a possibility that we might be dealing with external forces. Sum of all these forces are equal to change in kinetic energy produced. Now, think about the potential energy relation. What is potential energy? What is the definition of potential energy? According to the definition of potential energy, work done by negative of work done by conservative forces is equals to change in potential energy. Negative of work done by potential energy is equals to change in potential energy. So if we try to write work done by conservative force, it is equals to negative of potential energy. This is one thing. Similarly, if we assume that there is no external force acting on the system, no external force acting on the system, then we can say that work done by external force is also going to be zero. This is the second thing. So if we substitute both the relations into that equation, what we are going to have? We are going to have negative of potential energy plus work done by non-conservative force plus 0 must be equals to change in kinetic energy. So we can say work done is equals to change in kinetic energy plus change in potential energy. This is what the actual result of work energy theorem is. So in Bernoulli's principle also, we are going to use the same principle, we are going to use the same theorem to find out the energy equation for flowing liquids, the energy equation for liquids which are ideal in nature. Again, we are dealing with ideal fluids only, so we'll be talking about ideal fluids only.
sorry, sir.
So this
What does NCF stand for?
non-conservative forces.
Non-conservative. Oh, okay, okay. Why did you add zero to it, sir? Like plus zero?
I add 0 for work done by external forces. If there is no external force acting on a system, then we can say that work done by external force must be 0. Whereas there must be some non-conservative force, and those non-conservative force must be doing some work in the system, which actually responsible for changing in kinetic energy and changing potential energy of the system.
Okay, sir.
So let us try to understand that how we got the relation. If you understand that how you got the relation, there is no question that you feels like that you are not able to do. So in order to understand that how the relation is being used or how we got the actual relation, so first of all, let me give you a little bit idea. So Bernoulli's principle say that sum of all the energies, sum of all the energy is constant. Now what energies does it include? It include pressure energy, it include kinetic energy, it include potential energy. I'm talking about liquids only. So sum of all these energies must be constant as per Bernoulli's principle.
Okay.
Now, what is the relation? The relation is P plus half rho V square plus rho G H is equals to constant. So what we have to do is we have to understand that how we got this relation. How we can say that sum of all the energies for a flowing liquid, for a flowing ideal liquid is constant. So this is what we have to prove. This is what the Bernoulli's principle is. Now we are going to prove this particular relation. So just try to understand each and everything with a lot more concentration and focus. So first of all, I'm assuming that there is a ground, and with reference to this ground only, we are going to understand that how the pipe is positioned. So I'm taking different cross-section areas of a same pipe. For example, suppose So these are the two cross-section areas of a same pipe at different positions, at different height. So this is located at H1 height, I assume. This is located at H2 height. Now, the area of this cross section is A1. The area of this cross section is A2. The velocity of liquid flowing through this cross section is V1. The velocity of liquid flowing through this cross section area is V2. Apart from this, we already know that as height increases, pressure increases. So the pressure at this particular point, I am assuming as P1, as well as the pressure at this particular point, I am assuming as P2. And we know that P2 must be greater than P1 because we already saw that how pressure changes as depth changes or depth increases. So what we are going to what we are going to take here is that suppose the layer of liquid flows from here to here in some delta t time. So how much distance this layer has covered? V1 times t. Similarly, here also the same thing we are assuming. So liquid must have covered V2 t distance during t time, right?
Yes, sir.
So as we know, we are dealing with idle fluids. So A1 V1 must be equals to A2 V2. Although if this thing comes in FRQ, you again have to derive that how A1 V1 is equals to A2 V2. So keep that thing in mind. So we are going to calculate different energies now. First, we'll start with change in kinetic energy of the fluid. Let us do that. So first thing we are going to calculate is change in kinetic energy of fluid. So what is kinetic energy?
Delta K. So
What is the relation we use for kinetic energy?
it's equal to work. Oh, like the formula. Oh, half
Yeah,
mv
the
square.
formula. So we can write here it is going to be half mv2 square minus half mv1 square. As we are dealing with the idle fluid, so mass must be constant for both the cross sections area. So we can write is v2 square minus v1 square. In place of mass, what we can write? The same thing which we saw. So it can be written as a1 v1 delta t times density v2 square minus v1 square. This is what change in kinetic energy is. Similarly, we are also going to calculate change in potential energy. So how can we write change in potential energy? Tell me what we learned for change in potential energy.
The change in potential energy um would be like mgh1
Hmm. Right.
minus mgh2.
No.
Sorry, mgh2
This,
minus mgh1.
yeah. So as we can see that height of second area, the smaller one, is more. So potential energy of V point must be greater than potential energy of A point. So that is why it takes lot more energy if we have to transfer water to the greater distance or the greater height. Like for example, suppose it is a two-story building, then the energy taken by the water to transfer it to the top would be less in comparison to the building if it is four-story building. That is the case. It all depends upon how many floors are there. If there are two floors, it will take lesser energy. If there are more floors, it will take more energy. So potential energy at this point can be written as mg h2 minus h. Again, in place of m, I can write a1 v1 delta t rho g h2 minus h1. So this is what change in potential energy is. Keep these equations in mind, and how we got those equations also you have to keep in mind. See, these derivations help us to answer FRQs so well. If you understood these derivations well, then any kind of FRQ is there, we are able to answer them. Third thing, and the most important thing, We have to find out net work done on the fluid. Because the work energy theorem says the total, or you can say the net work done is equals to change in kinetic energy plus change in potential energy. So net work done on the fluid is what? Let us try to understand it. So net work done on the fluid is always equals to work done on the fluid at A, or this position. This is A, this is B. Whenever we are calculating work done, so just think about it. If we have to put water from point A to point B, do we have to do work, or if we have to put water from B to A, then we have to do work? At what point we have to do work? From A to B or from B to A?
We have to do work from A to B because we're working against gravity.
Exactly. So whenever we are writing net work done on fluid, so work done at A minus work done at B, that is what we'll write. Never do the opposite thing, because here we do B minus A, but here it should be A minus B. What is the logic? Because work done is always done against the gravity. If we are doing it B from B to A, then there is no work done because gravity does it all. If we just throw the
Yes.
liquid from the top, it will automatically come down. You don't have to do any work. But in order to uh, let it reach at the top, it is going to be difficult task. So how we can write net work done now? So work done at point A, if we try to write it, so work done is what? Force times displacement.
Yes, sir.
So I can write as F1 x1 minus F2 x2. Now what is F1? F1 is force. Now try to think about what is force in terms of pressure.
So force is equal to mass times acceleration, right? And
Think it in terms of pressure.
the pressure is how much like push. Pressure is like the push force. So pressure is like rho g h.
Pressure is equals to
Oh,
flow over
oh
area.
yeah, yeah.
So
Yeah.
force is
So
equals to pressure times area. So I
okay.
can write it as P1 A1 x1 minus P2 A2 x2. Now what can I write in place of x1?
Uh, V1. Oh, okay.
As we are dealing with ideal fluid, so A1 V1 must be equals to A2 V2. So we can simply write here, we can simply take A1 V1 and T common. So inside,
Yes.
in the bracket, we are left with P1 minus P2. P1 minus P2. So here, there is a final result. This is what the work done is. This is what the net work done is. So we got all the three things required to be substituted in the work energy theorem. Again, we calculated all these things to put them into the work energy theorem equation. Now
Yes, sir.
we'll substitute all the above equations in work energy theorem. You can also call it wet. So according to work energy theorem, work done is equals to change in kinetic energy plus change in potential energy. And again, you need to understand that how this relation came. If you substitute all the values, so work done is A1 V1 T P1 minus P2 is equals to half of A1 V1 delta T rho V2 square minus V1 square plus A1 V1 delta T rho G H2 minus H1. So you can write this thing as also delta T so that you won't get confused. If you take delta T A1 V1 common from both the sides, they will be cancelled out, right? So
Yes,
what we
sir.
are left, P1 minus P2 is equals to half of rho V2 square minus V1 square plus rho G H2 minus H1. Now simply open the brackets. So P1 minus P2 is equals to half of rho V2 square minus half of rho V1 square plus rho G H2 minus rho G H1. So let me just keep all the physical quantities having 1 on the left hand side and other side with the 2 marking. So P1 plus half rho V1 square plus rho G H1 is equals to P2 plus half rho V2 square plus rho G H2. If you just look at this equation, what you can say that energy at point 1 or point A must be equals to the total energy at point B. So can I say that the pressure energy, kinetic energy and potential energy for an ideal fluid flowing through different cross-section areas must be constant?
Yes,
Can I
sir.
say that energy for a liquid flowing through different cross-section areas must be constant? So
Yes, sir.
this is how the proof of Bernoulli's principle looks like. There is one more thing which we can do. We are supposed to find out total energy per unit volume. If we try to find out total energy per unit volume, so in that case, we divide the whole scenario with one thing, that is rho g. So in order to find out total energy per unit volume, divide the above equation with rho times g. So what we are going to have P over rho g plus half P square over g plus h is equals to constant. Now each term here has a significance. What significance they has? P over rho g is something we call pressure head. You must heard this term in the class. This is called pressure head. This is called kinetic head. So if specifically the question asks you what is the kinetic head of a given problem, then you have to calculate this. If it is asked you to calculate the potential head, it is going to be this. So this is how you have to understand. So in another form, this is another form of Bernoulli's principle, and according to which the sum of pressure head, velocity head, and gravitational potential energy head remains constant in the streamlined flow of any ideal fluid. Got it?
Yes, sir.
Now it has few limitations. Let us quickly talk about the limitations as well. So first of all, as I told you, it is not applicable for fluid not in streamline. For fluid not flowing in streamlined manner are not going to follow Bernoulli's. That is one thing. Fluid should be specifically following streamline flow. Similarly, we haven't considered the angular momentum of the fluid here, but in reality it is there. So Bernoulli's principle doesn't consider angular momentum of flowing fluid. So if it is not, in general it should be considered, and that is the limitation of it. In reality, whenever we are dealing with fluids, we do consider the angular momentum of fluid. Second thing, Bernoulli's principle is only applicable to incompressible fluid. If fluid is compressible, then it is not going to follow the Bernoulli's principle. That is another limitation of it. Because if it is, if we are not considering incompressible nature of fluid, then we will not be able to account the elastic energy of the fluid. That is another case. So here there will be another energy head that would be added if the fluid is compressible. So we can say if fluid is compressible, we have to take elastic energy of fluid. Whereas in general, we are not taking or dealing with any sort of elastic energy because we are considering that fluid is incompressible. There is no compression. There is no compression in the fluid. Again, fourth and the most important point. Fourth and the most important point, we are considering that there is no loss of energy due to friction, but that is not the case. In reality, there is a friction. So we'll simply say it is the biggest limitation you can say. No loss in energy due to friction. This is what we are considering, but it is not the case. Energy loss will be there for a fluid because of friction. And this is the reason why we generally don't see water. Hmm, I should not say that. So that is what you have to keep in mind. These are the limitations of Bernoulli's principle. Does this make sense? Does this make sense?
Yes, sir. Yes.
What were you doing?
Yes, sir.
I was asking what are you doing?
Nothing, sir. I'm just very tired, to be honest with you.
All right then. Let's do one thing. Let's keep it till here only. This is the main
Oh,
thing that we have to deal with. In FRQs, the derivation part can be asked. We need to understand what we have done.
okay,
What is the
sir.
equation of continuity? How it is applicable? All you need to take into account. And
Okay, so
from next time onwards, we'll be doing class at 7 p.m. IST. That is 9:30 p.m. SGT.
okay, sir. I can do that. Also, one more thing, sir. When my teacher
Yeah.
was deriving the Bernoulli's equation, right? He
Hmm.
just showed us the conservation of energy equation and just divided everything by volume. Is that also fine?
Yeah. Like he divided the equation with this, like this equation by volume.
Like all terms by volume. Yeah.
Yeah, that is also the case. If you divide each and every term by volume, what will it give you? It will give you energy per unit volume. It can be asked sometimes to give you energy per unit volume, or that is a simpler case. Like this is the part we generally use to explain small bits. Like for example, what is energy? What is kinetic energy? Kinetic energy is half mv square. So if you have to
Yes.
find kinetic energy per unit volume, it is going to be half mv square over volume. Now, what is
Okay.
volume? As we know, density is mass over volume. So, volume is going to be mass over density. So, if we substitute the same thing here, half of mv square, volume is mass over density. So, mass and mass will cancel out. So, we'll get half rho v square. This is what kinetic energy per unit volume is. So, it
Okay,
is
sir.
also called volume head. You can also call it kinetic energy head, not volume head. You can also call it kinetic energy head. So, you can use that also. But it doesn't give you the sense of that how energy is conserved. It is simply explaining that kinetic energy per unit volume is this
Okay.
generalization. But we
Okay.
generally don't use this to use in derivation part. Similarly, you can also find out potential energy per unit volume. So potential energy is nothing but mgh. So potential energy per unit volume is going to be again the same
Yes.
mgh over. I'm simply writing m times density, m over density. So mass will cancel out, so we'll get rho gh. So this is potential energy per unit volume. We can call it potential head as well. Similarly, pressure head, the same thing we are going to do with pressure head as well. So pressure per unit volume, that will give us excess pressure, to be honest. So if you try to write work done here, so work done is nothing but force into distance, and
Okay.
force can be written as pressure times area times distance. So pressure is P. You can write pressure as P, area as A, distance as X. So area times distance is volume. So if you have to write pressure energy of volume, this is what you can write. This is what we call pressure energy of volume.
Okay.
So you can use these things, and yeah, you can do that. You can use that.
Okay, sir. Oh, thank you, sir.
All right then. Take care.
Okay,
See you
sir.
in the next class.
Thank you. Bye bye.